Hundreds of billions of dollars just went into an AI data center. It's finished. The GPUs are installed. The servers are ready. And it can't turn on. Not because of a chip shortage, not because of a software bug, because of a single piece of equipment. It's not a GPU. It's not even a semiconductor. It's a transformer. Let's actually explain what that means, because it's stranger than it sounds. Picture this. A data center gets built. Every server rack installed. Every GPU plugged in. And the lights don't turn on. That's happening right now, across the US, at a scale most people have no idea about. One recent industry analysis found something wild. More than half of the data centers planned for this year are at risk of delay or outright cancellation. Not because of chips, because of missing electrical equipment. So what is this thing exactly that's holding back a trillion-dollar industry? Think of it like the pressure regulator on a water main. A power plant generates electricity at an enormous voltage, way more than any building could safely use directly. A data center needs that electricity at a much lower usable voltage. Something has to sit in between and step that voltage down. That's the transformer's entire job. Without it, the raw power from the grid is either useless or dangerous. With it, that same power becomes exactly what a server room actually needs. Simple concept. Simple metal box. Except it's not simple to build. And right now, it's the most fought-over piece of equipment in the entire AI industry. So why did this become scarce? Seemingly overnight. 4 industries are all pulling from the same supply, at the same time. AI data centers need them, at a scale nobody planned for a few years ago. Electric vehicles need them, for charging infrastructure spreading across the country. Factories need them, as manufacturing shifts back to the US. And the electric grid itself needs them, just to keep aging infrastructure running. All 4 of these demands used to be spread out over years. Now they're colliding, at the same time, on the same factory floors, competing for the same raw materials, which raises the obvious question. Why can't manufacturers just build more of them, faster? Here's where it gets genuinely difficult. These aren't off-the-shelf products sitting on a warehouse shelf somewhere. Large power transformers are custom-built, one at a time, for each specific site. Some of them weigh hundreds of tons. That's heavier than a Boeing 747. They require grain-oriented electrical steel, a highly specialized material with its own limited global supply. They require enormous amounts of copper. The same copper EV makers and grid operators are also fighting over right now, at the same auctions. They require specialized insulating oil to keep the internal components from overheating. And once built, every single unit has to be individually tested before it ships. That testing alone takes weeks. 5 years ago, a large transformer took 4 to 6 weeks to deliver. Today, that same order takes 80 to 210 weeks. Read that again, 210 weeks. That's about 4 years for one piece of equipment. Some manufacturers are quoting lead times stretching all the way to 2030 or 2031. There's actually a whole industry now built around helping companies navigate this mess. Consultants who track exactly which manufacturer has which slot open, in which country, for which delivery window. Because at this point, ordering a transformer is less like buying equipment and more like scoring concert tickets. You need to know someone, or move fast, or both. Here's a detail that makes this even messier. China actually controls roughly 60% of global transformer manufacturing capacity, which means a huge chunk of the fix for America's power problem sits inside the exact same geopolitical tension driving up chip prices in the first place. That's not a coincidence you'd want if you were designing this system from scratch. Some companies have started looking to smaller European manufacturers instead, in Portugal, Belgium, and Italy, since the big 4 American and German suppliers are so backed up. Those smaller players have shorter lead times, sometimes 20 to 30 months instead of 4 to 5 years. but their total capacity is tiny compared to what the US actually needs. It's a bit like trying to fill a swimming pool with a garden hose because the fire hydrant is already booked. So what does this actually look like for the companies building AI right now? Microsoft, Google, Amazon, and Meta are projected to spend around $725 billion combined on AI infrastructure this year alone. Nearly all of the major transformer manufacturers are effectively sold out for years. Hitachi Energy, Siemens Energy, ABB, GE Vernova. Siemens Energy is reportedly booked into the early 2030s. These four tech companies aren't just customers anymore. They're becoming buyers large enough to reshape the entire manufacturing industry behind them. One market analysis put a number on just how fast this is moving. The U.S. data center electrical equipment market is projected to jump from about $20 billion this year to $65 billion by 2030. That's more than tripling in just 4 years. And one industry estimate suggests data centers could account for as much as 40% of all U.S. electrical equipment demand by 2030, up from a historically tiny single-digit share just a few years ago. It gets worse if you look at gas turbines too, which is the other big option for backup power. GE Vernova's turbine backlog just hit 100 gigawatts. Their CEO said they're already selling reservations into 2029 and 2030, and they're running low on those too. Basically, if you're a data center operator trying to order a turbine right now, you might be waiting until the next decade. So what do companies do in the meantime, while they're waiting years for the real equipment? They improvise. Some are leasing giant fleets of diesel generators, essentially running a data center off the same kind of equipment you'd see backing up a hospital during a blackout, except at a scale meant to power an entire campus, indefinitely, not just for a few emergency hours. Others are quietly buying up used industrial gas turbines, whatever they can find, from decommissioned power plants. None of it is elegant. All of it is expensive. But it's the only way to keep a multi-billion-dollar facility from sitting dark while the real order slowly makes its way through a 5-year queue. And here's the line that should really stop you. Nvidia itself has publicly acknowledged slowing the expansion of certain AI clusters. Not because of a chip shortage, because of a power shortage. Read that twice. The company literally selling the chips is now the one telling you the chips aren't the bottleneck anymore. Which brings us to the actual scale of the problem, because transformers are just one piece of something much bigger. The real bottleneck isn't the GPU. It's everything standing between a power plant and that GPU. Transmission lines, carrying electricity across long distances, take years to permit and build. Substations, the facilities that manage and distribute that power locally, face the exact same equipment shortages as transformers do. And the transformers themselves sit at the very end of that chain. The last physical link before power actually reaches a server rack. Every one of these components has its own multi-year waiting list right now. In some of the biggest data center hubs, the wait just to get connected to the grid at all now stretches beyond 4 years, before construction on the actual site even matters. You can build the fastest chip in the world. If the electricity to run it can't physically arrive, none of that matters. So what happens next? A few things, all playing out simultaneously. Nuclear power is making a genuine comeback, and it's almost entirely because of AI demand. Every single major hyperscaler has now signed at least one nuclear deal. Let's actually go through them, because the details are wild. Microsoft is paying $16 billion to help restart a reactor at 3 Mile Island. Yes, that 3 Mile Island. They're aiming to bring it back online by 2027, just to power AI data centers. Google has committed to small modular reactors from a company called Kairos Power, targeting around 500 megawatts. Amazon invested $700 million in a company called X Energy for a fleet of small reactors, with the first phase targeting the early 2030s. Meta went the widest, signing deals across 4 separate companies, TerraPower, Oklo, Vistra, and Constellation, adding up to as much as 6.6 gigawatts of nuclear capacity. Together, these companies have now committed to nearly 10 gigawatts of nuclear power. That's enough to power roughly 7 million homes, just to run AI clusters. But nuclear takes years to actually deliver, no matter how much money gets thrown at it. So in the near term, the real answer is natural gas. New gas plants are being built specifically to bridge the gap, while nuclear and renewables slowly come online. There's also some genuinely interesting engineering happening around the transformer problem itself. A handful of startups are working on something called solid-state transformers, which swap out the traditional steel and copper design for power electronics instead. If that technology matures, it could eventually sidestep a lot of this shortage entirely, since it wouldn't depend on the same scarce steel and copper. That's still early though, more of a future fix than something solving today's problem. And underneath all of it, billions of dollars are now flowing into transformer manufacturing itself. Hitachi Energy alone has committed more than $1 billion to new U.S. production, including a massive new facility in Virginia expected to be the largest of its kind in the country. Siemens is expanding manufacturing in North Carolina. The U.S. government has even invoked the Defense Production Act, the same law used to fast-track wartime manufacturing, specifically to support domestic transformer production. None of this fixes the shortage overnight. Most of these new factories won't be fully online until 2027 or 2028, which means the bottleneck holding back AI right now isn't going away next quarter. It's going to be the defining constraint of this entire industry for at least the next several years. There's one more thing worth mentioning here, because it's the part that eventually lands on you personally. Utilities near the biggest data center hubs are already warning about rising electricity bills. All this new demand, all this scarce equipment, all this competition for the same grid, it doesn't stay contained inside a corporate balance sheet. Some of it shows up on your own power bill, whether you've ever touched an AI product or not. So here's the actual takeaway, and it's bigger than one metal box. The AI race was never really a chip race. It's an infrastructure race. Every headline about GPUs, model sizes, and training runs sits on top of something far less glamorous: steel, copper, insulating oil. A physical supply chain that takes years to expand, no matter how much money gets thrown at it. Picture the data center from the start of this video one more time. Every server rack installed, every GPU in place, and the building is dark. Now pull the camera back, past the data center, past the substation next door, past the transformer sitting quietly beside it, past the transmission line stretching to the horizon, all the way back to the power plant itself, miles away, generating more electricity than this one building could ever use. Somewhere in that entire chain, one small piece of equipment, custom-built, years behind schedule, is the only thing standing between all of it and the switch flipping on. $1 trillion in chips, waiting on one transformer,